I'm very happy that Orson agreed to talk a bit about his work on implementing algorithms and data structures in the real world. We talked about this in the context of sorting when we first started, and then we noticed that what he wants to say is actually more general than that. So while he's known for sorting algorithms as one thing, he did work on other things, and we'll probably talk about more general things, but I'm not going to say much more about this. I think I've been following your work, Orson, for a while. In particular, I've learned about this pattern defeating quicksort a long time ago. And I had worked on quicksort a lot. And in particular, this question, when you have duplicate elements in the input, quicksort is notorious for not handling that all that well unless you're extra careful. And people thought, okay, there's only some trade-off solutions. Either you do this or you do that, and neither is perfect. But I think you found close to the perfect solution. There's in pattern defeating quicksort, there's a solution that has little overhead when there's no duplicate keys, but also works extremely well if there are duplicate keys. And it's just nice and elegant, and there's no reason why it hasn't been found earlier, except that we were apparently waiting for you to do it.
Yeah.
So
yeah, I'm also kind of surprised it took that long.
that's the good ideas. They tend to be like this. Similar things I could tell about other algorithms, but I'm not here to speak myself. So I'm going to pass over to Orson for now. I will keep and mute the mic here for now and try to see on the laptop if there are questions. Because you're pretty set loud for the room to hear you clearly, the mic will probably cause troubles. If you have a question and you want to ask something, we'll do that at the end and collect everything. Would you like people to collect questions in the chat or Q&A?
I have the chat open. I have the Zoom Q&A open. I have the Slido open. I have everything on my second monitor, so I should be able to see it all. And of course, you can ask questions and or pass it through. So there will be plenty of opportunity.
Amazing. So make use of that. I haven't told people about the Slido. If you want to use it, maybe you can quickly share it. Otherwise, there's maybe the Zoom chat is enough.
Okay.
Okay, then over to you, Orson, and I'm going to take a seat here.
Thank you, Sebastian, for having me. My name is Orson, and I have a bit of a misleading title. It says from textbook algorithm to industrial strength code. I'm mainly going to be talking to you about performance. There's a lot more to industrial strength code than just performance, but that's essentially what we're going to talk about today. So who am I? I work at Polars, a data frame library. I work on query execution. I have written several sorting algorithms, and that's how Sebastian learned of my work. But also like hashing algorithms, some specific Rust libraries. I was lucky enough to be able to work together and improve the standard library sort in Rust. They adopted our algorithm, and I'm just generally passionate about performance. So I'm glad to get this opportunity to talk to you about it. So my goals of this talk today, first of all, I'd like you to understand the real cost of operations when you are programming. I'd like to bridge the gap from talking about, all right, this is O1 time or O1 space that you see in an algorithm class or on an algorithm description on Wikipedia, and actually move towards actual metrics that you can talk about. And using those metrics, I'd like you to be able to identify bottlenecks in your code and then show techniques to minimize those bottlenecks and costs. First of all, some assumptions. I assume you're using a low-level programming language, so like Rust or C, C++, or assembly, but and not something like Python or Java or Go or something like that. I'm not saying those languages are bad. I'm not saying you shouldn't use those languages. I'm just saying there's a lot of extra overhead and layers of abstraction if you're not using a low-level language. That makes it a lot harder to talk about performance, a lot more complex, actually. I'm also assuming you have modern consumer hardware. So that's a modern desktop, of a mobile phone, not a computer from the 80s, not some specialized hardware. And that also goes for which part of your computer. I'm only talking about general purpose processors today. So I don't have any advice for you what to do regarding GPUs, tensor processing units, or any kind of co-processing hardware you might see in a machine today. First, I want to talk about some basic costs of instructions that your processor executes. Your processor is superscalar and out of order. That means it can reorder the way it executes instructions, and it can execute multiple instructions at the same time. And those basic costs of executing instructions comes down to four main things. There's decoding of the instruction. What your processor runs is also data. It needs to load that data, it needs to decode the data, it needs to figure out what to do. There's latency involved of an instruction from the first cycle that data goes into the instruction until the last cycle when data comes out of the instruction. There's the throughput, typically notated in reciprocal, so the inverse of the throughput is essentially how many of these instructions can we execute at the same time, which is usually determined through execution units, which I'll cover a bit more later. So I want to just take a look at an instruction. This is an add instruction on Rocket Lake, an Intel processor, a bit older, but still relatively recent. And this is from uops.info. That's by the Saarland Informatics campus. They made this amazing tool called uops, which basically it's a research project that really finds out per instruction, what is their latency, what is their throughput, decode, execution ports, etc. So here we can see that the add instruction, it has a latency of 1. So when you start executing it as a result ready on the next cycle. A reciprocal throughput of 0.25, which means you can execute 4 every cycle. It's cheap to decode because there's only 1 micro operation, cheap to schedule. And it competes for the execution units on port 0, 1, 5, and 6. That's why essentially you can execute up to 4 per cycle, because there are these execution units that the actual instruction can run on. And there's 4 of them, so you can run 4 in 1 cycle. Sometimes it gets more complex than that, but in this case, it's that simple. Then we can look at a much more expensive instruction, this time on a Ryzen Zen 4 AMD chip. It's the division instruction. We can see that the result is ready in 9 to 19 cycles. What that means, sometimes that means the latency depends on the actual input. Maybe there's more complex inputs for which it needs to take more time to run. Sometimes this means that the operation has multiple outputs, and the latency might not be the same depending on the output that you want. You can execute only 1 every 7 cycles, so it's a lot more expensive than an addition. And it takes a bit more effort to decode and schedule the instruction. Unfortunately, the uops.info project has no execution unit information for Zen 4. Yeah, I don't know. Maybe one day we'll know that. Or you can read the actual manual, but nobody got time for that. Then let's look at a similar instruction, the unsigned divide instruction on Apple's architecture, on their Firestorm chips, which are found in the modern M1, M2, etc. processors. And we see that the same instruction, so the same operation, only takes 7 to 9 cycles, and you can execute 1 every 2 cycles. So Apple is a lot faster at executing division than AMD. Why? I don't know. I'm not a hardware guy. But it's important to keep in mind that these costs, they are multidimensional. So there's latency, there's decode, there's throughput, and they are platform dependent. So division might be relative to addition much more expensive on Intel than on Apple's ARM architecture. But I'd like to give you some, like a ballpark basic cost of instructions, which tends to hold. And I give them in cycles. So as processors get faster, the scales. Sebastian was very interested for me to talk about, like, all the things I'm going to talk about. Are they just for like this one machine, or do they hold more generally? These held for quite a while, and they might become more parallel, might go a bit faster, but these rough things I think will hold for a long time. The first is register to register moves. So moving data between registers tends to be free. That can be done in the reordering. of how the processor schedules its instructions, or if you have a function call that ended up inlined by the compiler. Then there's a whole bunch of small basic things that you wouldn't really be surprised by that are cheap. So it's initializing register with constant, addition, subtraction, OR, XOR, and all those like bitwise operators, comparisons, and bit shifts and rotations. Those are all like very fast, can execute many in parallel. Then it gets a bit slower if you want to shift or rotate by a variable amount, or if you gets even slower if you want to do anything with floating point. Then there's 3 to 4 cycles of latency, but you can still do quite a lot in parallel. If you then have more complicated integer multiplication operations or float comparisons, then also a bit slower, but still some in parallel. And then you get to the integer or float division, and then there's a huge gap. Division is actually really a much more complicated operation, not only for us humans, but also for processors. So that's really the only one you really should be looking out for, okay, one instruction might actually be expensive. A function call is actually only 2 cycles, but there's a lot of extra costs. There's the cost to restore your current state to the stack and restore it after the function call completes. You need to maybe store arguments, maybe read results to and from the stack. And there's a branch. I will talk a bit more about branches later, but essentially a branch is whenever you tell your processor, okay, now we're gonna execute a different piece of code. Memory allocation, now we're getting into the more expensive territory. If you do a small memory allocation, so anything less than 256 bytes, I found that it tends to be around 100 cycles. If you use a custom modern memory allocator, it gets around twice as fast, so around 50 cycles. So not that expensive, but you could still do, well, if you can do 4 in 1 cycle, you can still do 200 additions in the time you do 1 tiny allocation. So something to keep in mind. If you do a large allocation, I just wrote down, I did do a benchmark, I wrote down 2,500 cycles. It might be more, but usually about larger allocations, you don't really care about the time it takes to do the allocation itself. It's more usually the processing. But for small allocations, can matter a lot. Branches. So as I said, a branch is whenever your processor decides we're going to run a different piece of code. So that can be an if, it can be a loop condition, that can be a function call, it can be a switch jump. All of these are branches. All of these are, we were running this piece of code, now we're gonna go somewhere else. If the processor correctly predicts your branch, there's actually nowadays a little bit of machine learning in your chip, which depending on which address we are jumping from and which address we are jumping to, it predicts whether we actually do this jump or not. And there's all kinds of algorithms for that. I don't want to get into that. But essentially it says it's either yes or no. And if, for example, you have a check, which checks if an integer is negative or not, and it turns out for your input, it's never negative, it will very quickly learn that, and it will correctly predict it every time, and your branch is free. Or only costs 1 cycle for the comparison, like very cheap. If it doesn't correctly predict it, it will cost you between 15 to 25 cycles, which again, as we saw from the cheap operations, you can do a lot of work in that time. So we'll get more to like how to handle that. But for example, in sorting, where essentially every comparison that you do is ideally 50-50, we're trying to extract as much information as possible. If we're doing a comparison that's 99% of the time true, we're not learning that much from this comparison. So in sorting, this is a very important thing to take care of, because it could be the majority of your cost. Now we get to the bigger costs. And Sebastian said it was okay for me. This is the secret your professor won't tell you. In a lot of theoretical computer science, we just treat random access as O1. So it's constant cost. It doesn't matter how big your input is, accessing a random element always takes the same amount of time. It's not true of all theoretical computer science. There's theoretical computer science that actually is either cache oblivious or cache aware, etc. But in a lot of it, we just treat it as a constant time operation. Now for the reality, your processor has multiple levels of caches. The L1 cache, L2 cache, L3 cache, you might be familiar with it, but essentially it's just layers of cache on top of each other. And each cache gets smaller, but also faster. So if your data fits in L1 cache, if your data is in L1 cache, it only takes 3 to 5 cycles to load a bit of memory. If it's in L2 cache, it will take 10 to 15 cycles, which is still good. We're happy about that. We get a bit more concerned if it's in L3 cache, then it's 50 cycles, which is already 10 times slower than in L1 cache. And very important to note, this is latency. So how long does it take from I need the result now to how I actually get my result? And then once we get to RAM, it really becomes depressing quickly. It's 500 cycles to do a random access into RAM, which you can do a lot of work in that time. So random access latency is slow. It gets way worse. This is the only black page in my entire presentation. If you need to do a random access and I didn't even bother writing a hard drive. I really hope you're not using a hard drive for random access in 2025. But even if you have a fast SSD, it's still 100,000 cycles to do a random load of an SSD. If you are working on a compute cluster, even if you get your ping down to 1 millisecond from machine to machine, that's 5 million cycles. And if you have to access a bit of random data from the cloud, it has a lot of storage, but it also has a very long latency. 100 million cycles. That's an eternity. You can do so much in that time. Throughput, luckily, is a much more nice story. So throughput is, we're not looking for one specific byte at a random index somewhere, but we're looking at, for example, a stream of data or a whole block of data. So how much data can we actually pump through the system? And for L1 cache and L2 cache, it's about the same. It's 200 to 400 gigabytes per second. That's good. L3 cache, 100 to 200 gigabytes per second. Still happy with that. RAM, 50 to 100 gigabytes per second. Most of the time, that's plenty fine. Like usually you're not going to be limited by this. SSD is a bit more concerning, 2 to 5 gigabytes per second. That can actually be a problem, even for throughput-based things. So processing stuff in memory can be a lot faster if you can have the RAM available. And then for cluster and clouds, I really couldn't give you a ballpark. You can get as low as 125 megabytes. I mean, can even go lower if you really don't spend anything at all. But like a very typical is a gigabit connection, so that's 125 megabyte per second. If you spend enough money, you can get almost as much throughput as you want. It's just about how much money you want to spend. And with that, we get to our first advice I have, and that is to use absolute metrics with units. So it's very easy to fall into the trap whenever you're optimizing something or you're looking at performance to say this is 2 times faster than this, or 10 times faster, or 2 times slower, or whatever. It can be very easy to lose track of what your actual bottlenecks are because you're not expressing them in actual units. So units can be time in seconds or cycles, where I'm assuming throughout this talk that you have a 5 gigahertz processor. Some are faster, some a bit slower, but it's around that thing. So I like 0.2 nanoseconds is about a cycle. Your space can be in bytes or elements. Usually bytes is better for throughput, but sometimes elements make sense in the context. And then your throughput, you also want to specify in these units. So in cycles per byte, cycles per element, megabytes per second, like actual units that you can talk about. And I have some, and the reason why is that you can actually identify your bottlenecks if you use the appropriate units. So if your memory bandwidth limited, or you suspect your memory bandwidth limited, it might be useful to express your problem or what you're solving in megabytes per second. If you're a compute limit, you might want to be specifying it in cycles per byte or cycles per element, etc. And to explain why, I want to look at an example. It's very simple. It's what you get if you compile in Rust just the iterator.sum. And I benchmarked this on my my machine, and I got 7.4 billion elements per second. if we sum 1 billion elements of data. Is that good? No idea. These are just numbers, elements per second. I don't really know. I have no idea. If we specify it in actual units, so gigabytes of data, we have actually not 1 billion elements, but rather we have 8 gigabytes of data. And our throughput is around 60 gigabytes per second. Is that good? Well, now we can look at my machine. So I have some pretty nice RAM installed, a DDR5 RAM. And then if you look up the specs, you see the 6,000 megatransfers per second. It's a dual channel. The channel width is 8 bytes in DDR5. So my memory bottleneck is 96 gigabytes per second. But I also have a CPU, an AMD CPU, which has a interconnect between the processor and the memory controller unit, which clocks at 2000 megahertz and has a channel width of 32 bytes. So that limit is actually 64 gigabytes per second. So if we now actually go back to our example, is this implementation good? Well, it achieves 93% of the actual maximum achievable on my machine. So yes, it's really good. Like it's you're never going to get 100%. There's always a bit of overhead. So that's actually really good. But what about if we don't have 8 gigabytes of data? We only have 1,000 elements. Now it goes a lot faster. Now it does 43 billion elements per second. Again, because throughput and there's a lot more. It fits in cache now. I don't know. Is this good? It sounds like a big number. I mean, it's probably more than you need, but we can also look at it by looking at seeing, hey, it's 8 kilobytes of data. So we know it fits in cache, in L1 cache. And we're spending around we can process about 13.7 elements per cycle. Is that good? Well, we can look at my machine and we know it has AVX 512. Which has this VP add queue instruction, which can add 8 U64s in parallel. And we look at the manual and or on uops.info, and we can see it can be scheduled twice per cycle. So the absolute maximum this architecture can process is 16 elements in a cycle. So again, we see that we have around 86% of the maximum that we can possibly achieve on this architecture with this algorithm. So if you take into account, it's not an exact multiple of the vector size, and we also need to reduce the vector at the end, and there's all kinds of like little stuff. So that's actually also really good. So the automatic implementation that you get in Rust is both for a small amount of data and a really large amount of data is really good. So should we optimize this? No, it's a waste of time. Can't go faster. And we only figured this out by actually expressing our speeds and our throughputs and costs in actual units. So there's a couple of bottlenecks in the compute, on the compute side of things that you should probably be aware of. And I don't expect you to know what all of these are or remember them all, but maybe if I mention them once, next time you're looking at a problem, hey, maybe I'll look at that. That was a funny term. So there's the instruction decode. Sometimes you could execute many instructions at the same time, but the processor just can't decode them fast enough. There can be a dependency chain latency. So you're feeding a lot of results from one instruction into the input of the next instruction. And there's a very long chain of latencies that you're limited by. You can have execution unit conflicts. So we saw that some instruction can only execute on certain execution units. And if all of your instructions try to execute on the exact same unit, then you might be limited by that. You might be spending a lot of time on branch mispredictions. So you're constantly jumping around in the code and it's not predictable at all for the processor in which way you do that. So you're spending a lot of cost on that. It can also be really silly stuff. Like it can be heat production on some processors. If you just call the full AVX 512 multiply on all cores constantly, you're going to downclock a lot and you're going to produce so much heat that the processor just gives up. And that might actually be your bottleneck. That can be quite difficult to establish if you're not actually looking at your temperature. So it can be many things. And for memory, it gets even more complicated. So you can be limited by instruction cache. You are loading a lot of actual code to run, and your code goes out of cache. Your data cannot fit in cache. You can have store to load forwarding, which means that when you store a bit of data into memory, it takes there's a certain amount of latency before you can read back that exact data. So if you're storing and then reading back from the exact same location a lot, that can be a problem. You can have a problem with the prefetcher if you're so how your processor works is that if you how it achieves these high throughputs when you're reading like in a straight line a lot of data is that it sees, hey, they accessed position 1 and then position 2 and then position 4 and then position 6. We're just constantly going forward, so I assume that they want the next bit as well. So that's how you can hide these latencies, by the processor prefetching what you need before you need it. That works great, and that might work for 1 data stream, it might work for 2 data streams and 4 data streams, but maybe that's the limit. Maybe that's the maximum amount of data streams it can prefetch at the same time. Maybe with 8, it completely blows up. That can happen. Another bottleneck might be the translation leukocyte buffer. It would be way too much time to explain virtual memory versus physical memory in this talk, but essentially your processor memory addresses are fake, and your processor needs to know how to translate fake memory addresses into real ones. And that has a data structure. And if you have too many addresses, that data structure can become too large. As we saw earlier in the example, there might be an interconnect between your memory controller and your processor. You can be limited by actual RAM if you have slow RAM, or there's no internet connectivity, disk bandwidth, etc. Like a lot of potential different bottlenecks. And the thing about optimizing code is if you're optimizing a bit of code that is not your bottleneck, you're essentially wasting time. It's similar to Amdahl's law when it comes to parallelism. If it's not your bottleneck and it happens in parallel, it doesn't matter if you optimize it because you're still limited by your bottleneck. So that's why I think it's really important that optimization comes from understanding your costs and bottlenecks. If you don't know what you're doing, if you don't know where you're spending your time, how it's spending time, why it's spending time, you're kind of going in blind, and it's really hard to optimize code. So I have some examples now, some example techniques that you can apply. One of them is, well, we saw that you can execute multiple instructions at the same time. Let's say we're evaluating a polynomial, ax squared cubed, bx squared, cx plus d. Very simple. If you do this in what is considered the optimal form in terms of operations, you get the Horner's form, which only does 3 additions and 3 multiplications to evaluate this polynomial. But we saw earlier if a multiplication has a 3-cycle latency and an addition has 1 cycle latency, you get a full latency of 12 cycles. We can do more operations, so we're actually doing more work, but some of the work can be done in parallel if we specify it in the bottom form. So we can compute ax plus b at the same time as we compute cx plus d at the same time as we compute x times x. And all of a sudden, our latency is only 8 cycles. So we are a third faster just by changing the order of operations and making sure we can abuse instruction level parallelism. You might think your compiler does this automatically for you, and for integers that would be true. For integers, the compiler can do this kind of optimizations very well. For floating point, it cannot. Floating point addition and multiplication is not associative, which means a plus b plus c is not the same as a plus b plus c. So all of these optimizations, they are not available to your compiler. Floating points, these kind of stuff can really matter, also for accuracy, but that's too much to talk about today. Branch prediction. There are many different techniques to handle branch prediction. One of them is predication, which means replacing some kind of conditional with an unconditional kind of logic that implements the exact same thing. So instead of saying if x is negative, we add 1 to y, we can simply do the comparison, x is less than 0, convert this Boolean result to an integer, and add that to our y. Your processor also has dedicated instructions it's either called conditional move on Intel or C-cell on ARM. And essentially what it does is you have two inputs and a conditional, and it will select one of the two, but without a branch. Because the difference with a branch, you are doing one thing or the other. And with this, we are basically computing both results and then only selecting the result that we want afterwards. So again, we do more work. Here we are computing minus X, regardless of whether we need it or not. But that only takes one cycle, maybe 0 if we can do it in parallel with something else. So yes, we are doing more work, but then we don't have this branch, so we can just keep going. And that's a very powerful technique. Unfortunately, your compiler might undo your work in this. They are very clever, but sometimes they're not clever enough. So there's, for a lot of compilers, like in C and C++, there are like hints that you can give that you say, hey, this condition is unpredictable. I don't want an if, I actually want a CMOV here. But it's not a guarantee. Rust very recently added the function select unpredictable. That was I actually helped suggest to implement this, which actually guarantees, if possible, to generate a CMOV of C-select. So it's a very consistent way to create one of these instructions that selects one of two inputs. The third technique is address computation. So instead of saying, hey, if X is positive, we want to add it to the positive sum. If X is negative, we want to add it to the negative sum. We just have an array of two sums. And then we convert our logic into a computation of an address, in this case, sums plus 0 or sums plus 1. And then we add it to that index. And then later on, we can decode our answers from that. These are like the three main techniques, but you can combine these. You can, there's even more techniques. There's a lot of different ways of getting rid of branch prediction. And I want to give an example from sorting. So while implementing quicksort, you need what's known as a partition operator. And what this partition does is you have some kind of pivot value, and then you want to split your array into all the elements that are less than the pivot and all the elements that are greater than or equal to the pivot. So you end up with two partitions. And this is the inner loop of one algorithm. It's called Lomudo's algorithm that does this partition operator. And this particular variant is completely branchless. So how it works is we replace conditional moves, like we replace conditions, in this case with address computation and extra moves. So again, we do more work, but we don't have branch predictions. So how it works is we move one element. So I don't know if you guys can see my cursor. I hope you can see my cursor. If not, I don't know, follow along. So we move an element from I to J. And we know that this is an element that's bigger than or equal, creating this gap on the left. Then we increment our J, so to recognize that this is our new boundary position of where the greater than or equal partition ends. So that's our J plus 1. Then we move one unknown element into the gap that we created on the left, creating this scenario where we have our correct partition less than partition, we have our correct greater than or equal partition, and one element in the middle, which we don't know yet. And then we simply increment I conditionally. So if it's less than, we increment Y to move this unknown element into the less than partition. If it's bigger or equal to the pivot, we don't increment at all. And you can replace this condition with this predication. So we just increment Y by the result of this comparison. And this way you can do this partition operator completely branchlessly. It does more moves. So if you have very, very large data, it might actually perform worse. But if you have small data like integers or floats, then this is a lot faster, because we saw the branch mispredictions were like 15 to 25 cycles, and this executes in just that couple cycles. Another technique that can be really productive and that you also find in all the fast sorting algorithms is loop unrolling. So you have some kind of loop, we do something n times, and we have a body of this loop. And what we do is we replace this by essentially just the same body. You literally just copy paste it. Sometimes you can write it with a loop, but sometimes the compiler doesn't like that, and you literally just have to copy paste it 4 times or 8 times or 2 times, depends on the situation. And you reduce the amount of checks that you do of the condition. So that's one benefit. You have to do less conditions. But it also means that the processor knows that you're always going to run like these 4 bodies at the same time. And you can actually just create a lot of instruction level parallelism where there was none before. The iteration of the next body loop can already start executing in the body of the previous loop, which is a lot harder for even the superscalar processor to do otherwise. Can make a big difference, like 50% faster sometimes, or even more. Another technique to optimize your code, and this is the fun part. This is the part that everyone loves. There are the bit tricks and micro optimizations. You can give endless talks about this. The compiler actually often does these kind of tricks for you nowadays. But regardless, it's a lot of fun, and as we'll see later, it can still be very useful even in today's world. There's this amazing book called Hacker's Delight by Henry Warren. I would highly recommend it if you like these kind of low-level tricks of XORs and ANDs and masks and whatnot. And there's also this great page. If you just type bit hacks into Google, you'll find it. Would highly recommend checking it out. It's a lot of fun. I would also suggest learning from the compiler, like looking at what the compiler actually generates from your code. I do this every day while I work, or almost every day. Just double checking, hey, does this generate the code that I expect, or how does it handle this? Sometimes it really does strange stuff and you have to like correct it. I would really recommend the Compiler Explorer by Matt Godbold. It's either rust.godbold.org or cpp.godbold.org, or just type Compiler Explorer into Google. And you can have your code side by side. So on the left, you have your Rust code or C++ code or whatever. And then you have your compilation flags. And then you see the assembly, it splits out. So in this case, we're dividing by 5. So we load an argument into a register. Then, we have a very large number. Okay. And then we do a multiply and a right shift. That's not a division, or is it? So there's all kinds of tricks that all the compiler writers wrote for you into the compiler that you can learn from. One of them is we can replace division by a constant. We can replace that with a multiplication and a shift, sometimes an add. Standard algorithms, but there's a lot to learn in this regard. So I would suggest learning from the compiler. And now the big one, memory. So first, a quick refresher of terms. There's 2 kinds of locality. There's temporal locality, which means that if you access something, you can likely access it again in time. And there's spatial locality. So if you access something, it's likely that you access something near to it. Memory layouts in high performance computing is very important for multiple different reasons. And there's multiple different ways you can optimize it. So you can be optimized for throughput, which is temporal plus spatial locality, which means that if I'm accessing something here, I'm likely to access something before it or after it very soon. This is essentially you're beholden to the behavior of your prefetcher of your CPU or your disk or whatever. You want to optimize for this. This is by far the fastest you're going to interact with memory. You also want to put stuff that you access. If you access something, you want to abuse the fact that there's several layers of caches. So if you access something, you typically want to work with all that data as much as possible at the same time. And then once you're done with it, be done with it. You want to be aware of what you keep in cache. And there's finally, this is more niche. You want to optimize your memory layout for the minimum read size. So when something gets loaded from RAM to cache, that goes in multiples of a cache line. You cannot read 1 byte from your RAM. You only can read a cache line, which can be 64 bytes or 128 bytes. So this large latency penalty that we saw, if you're dealing with something that a byte-wise algorithm, that means that you can pay that cost 64 times less if you work in blocks of 64. And with disk, the blocks tends to be like 512 or 4 kilobytes. Depends a bit on the scenario. So databases want to optimize when they have to read from disk. There's no alternative, and it has to be semi-random access because we just type something into Google and we need to read something from a database. we probably want to make sure that if we have to load 4 kilobytes at a time anyway, that 4 kilobytes contains as much data as possible at the same time to answer a query. So some tips for that to achieve the memory layouts that you really want is use smaller types if you can. So if you're storing ages, maybe you don't need a full 64-bit integer. I don't think anyone is getting over 250 years old anytime soon. So maybe ages and years can be a U8, etc. Instead of a vector of bools, because bools for a variety of reasons are stored as straight up 8 bits in most languages. You can use a bit set so that you only actually you can store 8 bits in 1 byte. You want to place closely used things together. Again, as I said, you're reading stuff at the same time. So if you know if I'm reading A, I probably want B, you might want to put those together. And a big one is to prefer flat over nested structures. So if you don't need a linked list, probably don't use a linked list, use a vector. If you are making a graph, you probably want to prefer storing all the nodes in your graph in one contiguous vector and then using indices to access those, or my library swap map if you're using Rust. But that's a lot faster than doing pointer chasing, etc. So to make this concrete with an example, let's say we are storing people and we have an age, the city they live in, whether they're alive, maybe a bit born a bit, but and the relationship of their mom and their dad. If we do this on the left, we just define a struct with those fields, and we have a vector of that. Excuse me. Now we're storing 48 bytes per person, and we are duplicating the city for every person. So there's probably not that many unique cities. A lot of like I live in the Netherlands, so a lot of people live in Amsterdam or Rotterdam. I live in Leiden personally. There's 3 cities, you already cover millions of people with that. We don't need to store that same string millions of times. You could also store it like on the right. So we have the unique cities. Ages, we lowered to only use 1 byte per age. The city is now no longer stored duplicated for each city, but instead it's just a reference into unique cities using an index. We now store a bit set, which per person stores whether they're alive or not. So we only use 1 bit per person for that. And again, mom and dad have been changed from a full pointer to just an index because our system doesn't need to handle more than 4 billion people. Doesn't mean you can handle every person on Earth, but maybe that's enough. Maybe that should be U64 if you do need to handle every person on Earth. But this is 13.125 bytes per person. The 125 is because we only use 1/8 of a byte on average to store the alive bit. And the city is normalized. So this means we can at least store 4 times more data in cache before we have to go to slower RAM, or at least 4 times more data in RAM before we have to go to disk, etc., etc. I cannot give a talk about performance without mentioning SIMD. I don't have time to really get into it. You can give an entire talk about this to yourself. What is that for those who are unaware? Your processor has special, or most processors at least, have special instructions. They are called single instruction multiple data, or SIMD instructions. They typically widen the register. Usually a register is 64 bits on a 64-bit machine. They have wider registers, so 128, 256, or even 512 bits. These single instruction multiple data instructions, they execute the same operation for the whole register. So even though you might have 512 bits and we're doing an add, in the case of a 64-bit integer add, so you get like these fancy names here, MM512 add AP64. The AP64 means we're doing we're working on signed integers and we're doing an add instruction. It means that we split the register up in 8, interpret it as 8 integers, and then we add them. So we're doing 8 adds using 1 instruction. This makes the decode and schedule of these instructions very efficient. It's actually our processors. Circuits are very fast at executing and actually doing the operations that we need to do. Programming and efficient programming is really mostly about how do we get data into the processor as fast as possible and data out. Moving data around and loading data and storing data is much more costly typically than the actual number crunching that we need to do. Also deciding what we're going to do. That's also very expensive. So that's why SIMD can reduce those costs. They are very platform-specific availability. So not only, it's not enough to say I have an Intel processor or an AMD processor. You need to know the exact make to determine whether that processor supports a specific set of SIMD instructions. So it can be really annoying to deploy code that uses this. Sometimes you just have to assume that your customer or your client has like not a processor that's too old or a specific kind of processor. So it's usually not, I wouldn't reach for this immediately. What I would usually do is something called auto-vectorization. Your compiler knows that these instructions exist. If you turn on the right flags on your compiler, they can generate these instructions from your code. And they can do that in a lot of cases, not all, certainly not all, especially not if you're like shuffling data in unpredictable patterns. But if it's just, here's two large arrays, calculate a sum, or here's two large arrays, do the difference, XOR or whatever, they can do that. You do need to be aware of hidden control flow. For example, in Rust, if you just do an index operator in Rust, that will generate a panic if the index is out of bounds. So if you actually start inspecting the code on, for example, the compiler explorer, you will notice, hey, it's doing a check whether this index is in bounds. And this check can actually prevent auto-vectorization from occurring, because we need to do 8 operations at the same time, but the compiler needs to do exactly what we wrote. And if you wrote, we first check the first index, we then check the second index, we then check the third index, all of those for bounds checking, sometimes that can prevent auto-vectorization. So really inspect your code and see whether it occurs. But if the compiler can auto-vectorize it, I would highly recommend it instead of doing manual SIMD. The nice thing about SIMD is that it makes these tricks I talked about earlier. So these, the ones that you find in books like these or pages like these, it makes these valuable again. If the compiler can't auto-vectorize for you, then you need to apply all these tricks yourself. And then it's very valuable to know the tricks. Again, I also can't give a talk about performance without talk about parallelism. You could give an entire talk about this by itself. I'm just going to give a very few pointers. Prefer share nothing. So prefer that if you do parallelism, all your parallel tasks work completely independently from each other, and use message passing between the tasks rather than sharing data. That usually maps very well to divide and conquer, and that's usually your parallel algorithms all the way. So in my experience, at least 80% of all parallel stuff that you could do works with this paradigm, and I would highly suggest it. If you do have to share memory and have to do a fancy shared algorithm, then keep in mind that contention, that's your main worry when you're dealing with performance parallelism. Contention is in cache lines, not on individual bytes of memory. So if you're accessing 2 pieces of memory at the same time from 2 different threads, and you think, oh, but these are 2 different things, why are they contending with each other? Why are they slowing each other down? That's because they're on the same cache line. You need to actually physically add in your program waste extra memory to make sure they're not on the same space. And again, a couple just some hand wavy ballpark estimates. So if you have a normal load and store takes 5 to 10 cycles, uncontended. If 2 threads are trying to load and store to the same cache line, then that immediately blows up by a factor of 10 times to 50 to 100 cycles. And if they are both trying to do an atomic operation, so your processor has atomic operations that will really make sure we're doing, for example, add 1 in 1 atomic step. So it's not possible that only one of the threads added 1, or they started sharing the data, or all kinds of nasty stuff. So those operations, if you do those in a contending way, they actually need to lock internally in the processor, get like a lock on the cache line, and it gets really slow. Like you can see like 200 times slower than normal accesses. Maybe the most important tip, if you're doing performance, your compiler typically needs to be told to actually optimize your code. If you're just debugging something, you don't need to do this, but if you're actually interested in performance, you need to turn on your typically called release mode flags. So you actually make sure the compiler is making your code as fast as possible. This can easily make code 100, 1,000 times faster. It's not negotiable. You have to turn this on. Finally, I talked about bottlenecks that allows you to like identify or talk about actually on the hardware side, why is my code slow? But you usually don't have only one tiny function. You usually have an entire project, and you need to find out in the project where I'm actually spending time. And you do that through profiling. So you run your code and you attach special software that will tell you where you're actually spending your time. To do this, you need to, again, add special compiler flags that turn on these debug symbols so the tools understand your code. And there are many different tools. I would highly recommend a tool called Samply. This tool, this tool is so good compared to the competition, and it's free, that I felt obligated to explicitly mention it in this talk. It's what's known as a sampling profiler, which means that it will run your code, and essentially at random times, it will just very briefly pause your code, check where it is, and then continue running. It takes these samples. You just literally type samply record followed by your command, and then once it's done, it will open an interactive explorer in your browser. You can zoom in on bits of code. You can zoom on certain times. You can look through the call stack. You can this is an actual real profile from me at work, looking at Parquet decoding. It's amazing. Like if you have a large program, you can very quickly find out where exactly you're spending time on which thread running your code. And then finally, once you actually know where you're spending your time and you need to improve it, you need to measure. Measuring is very hard. At every step of the way, the compiler is trying to optimize your code in ways like if you'll try to profile how long does it take to sum these integers, the compiler will do that compile time for you and just inline the result. So you're just saying, hell, I just summed 1 trillion integers in 0 seconds. That's very fast. So you need to avoid the optimizer optimizing out the part that you want to test. You need to avoid measurement overhead, which, because an add is only one cycle, that's 0.2 nanoseconds. Your timer can't determine 0.2 nanoseconds. So you need to repeat your micro benchmarks. There's, especially if your benchmark takes into account anything with memory, you need to avoid all these caches that try to make your code faster, but they can hide inefficiencies. So you need to maybe clear the file cache because your operating system automatically caches files that you load into RAM. You maybe need to force spill your memory cache, etc. And it gets worse. Repeating your micro benchmark is in direct conflict with avoiding cache effects. Your disk has a cache of its own. You are running other processes on your computer. If you are running this in the cloud, there might be other people running stuff on that computer. The computer might overheat. The compilation, shovel, etc., etc. Like, I don't really have good tips for this. It takes a lot of experience. Just be aware that measuring is very hard. You need to get good at it, and yeah, despair. And honestly, that was my talk. So are there any questions from the audience?
Thanks a lot for the talk. I have to explain this. This is the very German style of applauding after a talk. You knock on the table. That's what we do. Don't
Okay.
People are used to this. I suggest we take questions from the room, and you have a watch out for the.
Yeah, I'm looking at the chat and the Q&A and stuff. Yeah.
I'll have to pass around the mic.
So I don't know if you can hear me.
Yeah, I can.
Yeah, okay. So how would you get so dive into like low-level programming and also like go in really deep down into how the compiler works and making your way through all this? Because to be honest, like you just sound to me like a wizard. That's how I would define low-level programming programmers. I just kind of want to know like your journey into this, because I've been only dealing with a lot of high-level programming languages, and it's mainly a wonder for me like how you would get involved in this and get good at this.
Practice, and the only way you can really practice is if you have something you're interested in. So for me, I don't know, I've always been interested in making things fast, and I am not a huge fan of magic. So as you say, like I may seem like a wizard. if something seems like magic, it just means you don't understand it well enough yet, and you actually need to dig into how it works. And really, I don't really have like, there's no magic trick. There's no do this and all of a sudden it opens for you. It's just reading code. It's experimenting, doing a lot of experimenting, understanding why. Not just like, oh, that's funny, I didn't expect that. Try to figure out why did this happen? Why was this slower? Why was this faster? And I mean, sometimes you run against a brick wall. Sometimes it's literally just faster and slower, and you have no idea why, and you can't figure it out. Sometimes you can ask other people. Don't be afraid to approach people that you know that maybe know more, or in Discord chats or Stack Overflow, etc. Try to really dig in, and yeah, an expert is only someone who's made every mistake there is to make.
And I got a follow up. So what about contributing to open source project? Like how widespread is optimization into this low level stuff on like communities like GitHub and projects out there?
Yeah, that really depends on the community. The thing is, like, especially if you're doing like really low level optimization, there's this saying that like 99% of the time is spent in like 1% of the code, and usually a project has already optimized that 1%. I'm not sure if going into open source projects with the goal of I'm gonna get good at performance optimization is the best way, because usually there's a very high standard in open source project, either a very high standard or a very low standard. And if there's a very low standard, they probably don't care about performance anyway. A lot of projects don't care about performance, and for a lot of projects that's fine. If it's literally just a tool to show a ping graph on your like, if it goes wild, like we humans can't tell the difference between 1 microsecond and 1 nanosecond, even though that's a massive difference. If you do that a billion times or a trillion times, like we can't tell the difference. So for a lot of software, it doesn't matter. I really would suggest find your own pet project and really try to make it as fast as possible. So something that you're interested in, and optimize that. Yeah.
All right, thank you.
Yeah, so the buttons on this one are a bit fiddly. Can you hear us again?
Yeah, I can hear you. There's a question from the chat I can quickly answer. In the chat, it asked, you said that it's good to keep types as small as possible. For integers, I read that it's preferable to use the typical size of your CPU. For example, in a for loop, it's better to have a signed integer as a loop variable instead of a short. Is this correct? It depends. It's really, it's hard to say. It's typically fine to just have, if it's like a variable that you're programmed with and the variable stays in a register, you can just make it a register sized variable, and that will never, like a 32-bit add is the same as a 64-bit add in terms of cost. For multiplication specifically, it can make a small difference, but typically I would say that it doesn't really matter for in-memory. So you can do the conversion when you load the memory. Like, let's say it's a byte and you can load in. I would more focus on if it stays in memory and it doesn't have to go. So if it stays in registers and it doesn't have to go to memory, I would more focus on correctness of the type and making sure like the sum doesn't overflow than worry about the type that you represented with the variable.
Questions in the room? I have a question, well, many, but I'll try to restrict it to a few, maybe more broadly accessible ones. One question is for the bottleneck analysis that you showed.
Yeah.
In the tiny example, I guess this is fine to do manually. Is there any help in terms of tools to automate this partly? I guess profiling first to find the code that really causes the major slowdowns.
Yeah.
And it still sounds daunting to me to do this manually.
So there is on Linux, there's a tool called perf, and perf can really dig into all kinds of performance statistics. So it can show you how many branch mispredictions a piece of code had, or how many page misses, like all kinds of very detailed statistics. They can help you to rule out bottlenecks. Like if it shows there's no branch mispredictions, you don't need to look at that. And typically this calculation, you don't really need to dive this deep. Usually, like, you very quickly learn, oh, my throughput is 1 megabyte per second. Then you know you're not limited by the hardware. Like it's impossible. You are limited by, unless you're doing an insane amount of compute per byte, you are not limited by how your memory, for example. And I still think it's very good. It doesn't get that daunting if you just do a quick paper napkin calculation, like, oh, how much data am I processing? 1 megabyte per second. Oh, that's really not that fast. I can do thousands of times faster. So this is much less an exact science as it is quick paper napkin math.
Other questions?
Hi, I have used both pandas and polars in the past, and
Yeah.
I like it. And I want to ask if you have like any personal stories or what worked well or didn't.
Ooh, get off the dirty stuff.
Okay. I mean, I've done a lot of stuff in polars. So one of the big successes that I implemented in polars is the streaming engine, which really works with this throughput versus latency and making use of cache. So for for the people who don't know what polars is, so polars it's where I work, and it's a data frame library, which essentially means it lets you write a query for, you have a bit of data in a data frame, it lets you write a query like, give me the sum of profits. Something very simple like that. But you might have more data than you have RAM on disk, or you might have a very large amount of data, but it still fits in RAM. So you might have gigabytes of data and you want to know the sum of that. So you can just write in Python, you can write your query, and then it's up to us to execute this query as fast as possible. So for example, the streaming engine, how it differs from the old in-memory engine. The old in-memory engine, if you had add 1 times 2 dot sum, all these kinds of like operations, it would do it on an entire column. So if you present your data, if you view your data as a table, it would do it on an entire column at a time. So it would add 1 to all the integers in one column, then it would multiply all the integers in one column, then it would sum all of them. The difference is that the streaming engine, it splits up the data in the data sources. It splits it up into small bits we call morsels. And the idea is that 1 or 2, 2 or 3 morsels fit in at least L3 cache, which means that and then those morsels flow through our data processing pipeline step by step. So we add 1 to this morsel, then we multiply everything in this morsel by 2, and then we sum everything in this morsel, which means that you can stay in this cache throughput rather than in the RAM throughput, or stay in the cache latency instead of the RAM latency. So that's like it made a huge difference for a lot of queries. It goes faster, to make it go faster, rather.
Other questions? The back of the room. Do you want to comment on how it is to work at a company that has as the main product something they give away for free? So some some concern connected to this, or how do people view this?
I mean, so our main product, I don't actually work on our main product. That's right. I mean, it's a bit hard to say. So Polars is not our product. Polars Cloud is, and Polars on-premise, which essentially means you run Polars on cloud machines, or you run Polars on on-premise, a cluster that you already own as a company. And that's the thing that we sell. I don't really think there's a conflict or like there's a worry about that. I mean, there's commercial interest to like have a managed cloud product, or there's commercial interest to just be able to write from a laptop your query, and then it automatically runs on your company's high performance cluster, etc. The open source product is and remains free, and it's actually great because it actually gets Polars into the hands of people, and they can use it and get used to it, and then go to their employer. Hey, I would like to use Polars. Oh, but we want to have it managed in the cloud. Oh, well, wouldn't you know? We have Polars Cloud for that, etc. But I personally mostly work on the actual open source component myself.
I have one final quick question, but I want to give people the chance to do another one. Well, a quick one is, are you related to Tim Peters in any way? We have to get
Not that I'm aware of. No, not coincidence.
Somehow there's something in the name that drags people into sorting, it seems.
Maybe.
Maybe.
Yeah. No, as far as I'm aware, we're completely unrelated. I don't think we've ever met either. So, yeah.
Maybe that's something to fix at some point in the future. If there are no further questions, also online, I'd like to thank you again for the deep dive into performance code. I learned a lot. A whole list of cool tools that are new. I didn't know Samply, for example. That was very valuable. I hope everyone in the room also took something. Thanks a lot.
You're welcome. Thanks for having me.